Okay, so it seems that YouTube is active.
Yes, it is.
Oh, perfect. Okay, so I think we can start. I mean, surely many people will connect in the next minutes, but okay, time is flying, and I think we can go if Harald, you agree. So we have. Oh, let me switch on also my camera. Thanks for registering and connecting to the 11th AT Symposium. So you see from the agenda that we have today a introductory, a welcome session, and then we will have the other sessions in the next days. So just to begin, since it will be a very large meeting, we have the official welcome from Edwige, since LAP is virtually hosting this email, and also we have a list of technical recommendation for participating to this video conference. And then me and Harald will start with the introductory talk that we shared in two. We divided in two, and then we'll have all the other speakers. Harald, if you want to say a few words, and then we just start with the technical and welcome from lab.
Yes, good afternoon or morning or evening, wherever you are on this globe. Many thanks for registering. We are overwhelmed with the number of participants. It's 710 officially registered participants. That is by far the largest ET symposium that we ever had. Even the number of participants on this channel now with 183 is larger than the usual ET symposium. That's great. We are really enjoyed that the interest in Einstein telescope and gravitational waves is so big. And we'll start after Edwige has told you a little bit about the technicalities. We'll start with an overview of the Einstein telescope.
Thank you. So please let me just share my screen. So we are very happy to welcome you all for this 11th Einstein Telescope Symposium. As already said by Michele and Harald, I'm just going to take a few minutes. So we would have been very happy to, to welcome you here at LAP, where you could have enjoyed our nice place and landscape, but it's also very nice to have so many people on the video conferencing system, and it will allow many more people to follow this symposium, so it's very nice this way as well. Just a few words on the technicalities and good practices. So please make sure that you keep your microphone off if you are not speaking. For the speakers, do not forget to stop the sharing once you are done with your presentation. And for the questions, as you are many, we suggest, we would like you to ask you to use the raise hand tool or the chat tool. I will explain just after how to use the raise hand tool. And please also lower your hand after you have asked the question. And I remind you that if you just want to listen, you can also follow online on LAB's YouTube channel. So just one more thing on the raise hand tool. If you are not familiar with Zoom, when you go to the bottom of your screen, you will see on the menu, you click on the participants, and then you will have on the right the list of participants, and on the bottom right, you have the raise hand button on which you can click. And so that's on this way. It's very easy. And when you are done, you have your hand which will appear next to your name, and you can click on it to lower it down. All right, that's all. So I wish you a very nice symposium, and I leave you with Michele and Harald for this session.
Yeah, thanks very much, Edwige, and thank you very much for organizing all this, and for even organizing it twice, because the organization for the first meeting, which fell victim to the Corona crisis, was almost done. So you had to, unfortunately, spend all the work without the merits, without the success of us all meeting there in person. So thanks a lot.
Okay.
Yeah, Michele, go ahead.
Okay, so I'm chairing the semi-talk of Harald, and he will chair my half talk. And so I suppose that you, Harald, are sharing the screen, because in this moment I have just one. Okay, I see your screen, and just a second. I have a small problem in seeing your screen. Let me solve it. But I think you can start, and so you have more or less 10 minutes, but even more if you want. And
according to my computer, screen should be visible now.
Yeah, it is. It is.
Okay.
Thank you.
So we divided the introduction, the status, and S3 proposal presentation into two. And because there are quite a few members of the symposium today who are new to the gravitational wave world, I'd like to start a little bit in the past, kind of with where we came from before telling you where we want to go to. Let me check why this doesn't work. Aha, there we go. What we've now got is the Advanced Gravitational Waves Detector Network, which is the second generation. So after the first generation, which was LIGO, GEO 600, and Virgo, these detectors have been upgraded to what is now called the Advanced generation. Advanced LIGO, 2 detectors, one in Hanford, one in Livingston, Louisiana, both 4 kilometers. Advanced Virgo, close to Pisa, Italy, with 3 kilometers. There is the GEO 600 detector, although in terms of sensitivity, it doesn't play a big role anymore, especially in the low frequency range. The 3 other detectors I mentioned are way more sensitive, but new technology is being investigated in GEO 600. And recently, in the spring of this year, a new underground detector in Japan, Kagra, became online and participated in data runs. Talking of data runs, we are, as we are now in the second generation, in the advanced era, we started counting the observation runs anew. The first observation run 01, you have all heard of, because that at the very beginning of that one was the detection of the first gravitational wave. And then in the subsequent observation runs, even more gravitational waves were detected. In between all these observation runs, the detectors were improved, sensitivity was improved. And at the right here, you can see the sensitivity of the detectors, of the LIGO and Virgo detectors, within the observation run number 3. And what is depicted here, I hope you can see my mouse moving around here. That is the range up to which a binary neutron star system, emerging binary neutron star system, can be seen with a signal signal of noise to noise of 8. So it is 140 megaparsec for the very best. That was the LIGO Livingston detector. It's about 110 for LIGO Hanford, and it's about 50 for the Virgo detectors. I see that down here. I made a mistake in telling what this is for. And in these observation runs, a number of coalescing binaries has been observed. So there were 11 binaries observed, the gravitational waves of the binaries observed in the first two observation runs, 01 and 02, and 39 new ones from the first half of the third run of 03A, as it is called. The data of this observation run are analyzed in two halves, and the first half of this observation run is now done, and the second half is now being analyzed and published soon. What is displayed here is all the individual mergers, and along the vertical scale is the mass of the components and of the result in terms of solar masses. So what you see down here is neutron stars. The neutron stars are to be expected in that range, and the black holes were, before the detection of gravitational waves, only known to exist in about this range. So it was a surprise to find black holes in that mass range up here. And even in the new observation run in 03A, there were a few surprises. For example, down here, we've got a component of the merger where it is not quite known what it was. It was either a heavy neutron star or it was a very lightweight black hole. It's not clear yet what it is. That remains for later observations. And also at the upper end, there were surprises, because in this range indicated by this faint white bar here, by this box, you wouldn't expect black holes from normal stellar evolution. So these that originate, they start from up here. It's not quite known how they were formed and why they do exist at all. The heaviest observed was this resulting black hole here with a mass of about 150 solar masses. And despite the large number already that we get from these observation runs, it's now with the current sensitivity, it's about 1 per week. There are lots of other sources that we expect to exist but haven't seen at all. Some of these here are specialities. I've mentioned one of them with this lightweight, who knows what it was, and the more heavyweight, the heaviest here of all. But there were also some that were very asymmetric in masses, like this one here, and you can deduce other parameters from these nicely. But as I mentioned, there are lots of other sources that we expect out there that should emit gravitational waves. Supernovae, for example, coalescing binaries we have seen. Pulsars, a little bit uneven with an ellipticity, and we can already conclude that the observed, or the rather not observed ones, but the ones from which we know that they exist, are very round objects, the neutron stars. But also from the very early times of the universe, a tiny fraction of a second after the Big Bang, we expect gravitational waves to be emitted way before the earliest photons that we can see, or even neutrinos. I'm sure that you will learn a lot more about the possibilities of what the future will bring in that regard by the talks later on, for example, from Michele. Okay, so these sources we haven't seen yet, and that is why we are pushing forward in the sensitivity. These faint curves here as an amplitude spectrum, as an amplitude strain spectrum, show you where we are right now. And the brighter curves here are what the design of the current detectors is. This is what we will reach once all the technology that is foreseen will be implemented. The technologies for these detectors have not yet come to an end of what is technologically and physically possible. So we hope to, in the end, with these with these detectors by improving subsystems to reach a curve something like this. And what we have to work on, which noise sources we have to reduce, which subsystems we have to improve in which way, is told to us by the noise budget of the current detectors. As a function of frequency, here is again the amplitude spectral strain sensitivity. So this is the black one is the resultant sensitivity. And below in colors, you can see what this is composed of. And in the high frequency range, you can see that this is purely quantum noise. So what you have got to do there is increase laser power or use squeeze states of light. And then you can lower this end of the sensitivity. In the mid-range, it is similarly limited by quantum noise, but also by coating Brownian noise. That is the coating that makes the mirror highly reflective, that exhibits tiny fluctuations on the surface called thermal noise, that mainly comes from mechanical losses, and that needs to be improved to improve the mid-frequency range. And in the low-frequency range, you can see that there's quite a bunch of different noise sources. Quantum noise, that is radiation, pressure noise back-acting, the light is pushing, is shaking the mirrors, but also suspension, Newtonian noise, and quite a lot. So this variety of noise sources means that essentially we have to work on every detector subsystem. This is a sketch of all the detector subsystems that play a role in the sensitivity that are important, and essentially on all of them we have to work, and we have to improve those. I mentioned that between the data runs, between the observing runs, the subsystems are being improved. We are now here, and for the next data run 04 and also for the subsequent one 05, subsystems will be improved to improve the sensitivity. From then on, we do not call it the advanced generation, but the advanced plus, so the kind of advanced, and it is then denominated with an A plus. But at some point, the infrastructure of the existing detectors will reach a limit. First of all, it will be old. So by the times indicated here, these systems will be 30 years old, and then they start to fail. These infrastructures don't live forever. And also they reach a limit in performance due to self noise. These infrastructures were not made for ultra high sensitivity. They were made for the design sensitivity that we are now approaching. And the third factor, any further upgrade would require significant changes in the infrastructures to avoid the self noise, to improve the infrastructures, which would cause a huge downtime. And of course, especially now that we are entering the era of gravitational wave astronomy, scientists are eager to push forward and to continue. So for the third generation, for a next generation, we started to think about what to do about in 2004, and from 2008 to 11, we have conducted a conceptual design study to design a new telescope, a new infrastructure that will reach about an order of magnitude better sensitivity, the Einstein telescope. We did a lot of small studies in the meantime until a couple of years ago. We ramped up the efforts again and updated the design report. Here you can find quite a set of relevant ET documents if you're interested. Just quickly over the main technical components.
Time is going, so
time is going. I'll hurry up. Most of this will be repeated anyway, so I'll quickly skip over it. The one key ingredient of the Einstein telescope is size and the triple nature of the interferometers in a triangular way. Another one is that we will split a single detector into two interferometers, and that way disentangling two challenges. high power for the quantum noise at high frequency, and cryogenic operation at low frequencies to cut down noise sources there. That has a number of consequences that will be talked about later. In essence, we will get one set of low frequency interferometers, one set of high frequency interferometers, and if we combine these two, then that is the sensitivity curve that we always show to you as the Einstein telescope sensitivity curve. The Einstein telescope hopefully will not be solitary then in the world, and there are other projects like Cosmic Explorer. Matt Evans will soon tell you about this concept, even larger, but on the surface, in contrast to the Einstein telescope, which will be built underground. So we hope that in the end, we will have new detectors, Einstein telescope here in Europe, Cosmic Explorer in the US, maybe a third large one in Australia that would be very beneficial for triangulation of the sources. And we can't foresee yet how the other detectors will then, which ones will be in operation. For sure, the new one, LIGO India and Kagra, but we can't foresee how the infrastructures of those will work. The sensitivity goals that we intend to reach, you see, we are up here now. This is the goal for A+. So at the end of this timeline that I've shown you, that goes into too many details here. Cosmic Explorer and the Einstein telescope will be down here, an order of magnitude better and quite an extension in frequency range. That will allow us to almost hear the whole universe in coalescing binaries. We will see all the black holes that we expect to be there, and most of the neutron stars as well. You can see here that we will reach a redshift of 100 with these detectors of the third generation. You will hear more about this in subsequent talks. So in the late 30s, gravitational wave astronomy will hopefully have taken a big step forward, lots of new sources, lots of new science. And if everything goes right, then the new detectors will be in sync with LISA, the space-borne gravitational wave detector up there somewhere. Thanks.
Okay, thanks, Harald. So we will take questions after my part. So now, if you stop sharing the screen, I will try to share my screen.
Okay, there you go. Had trouble finding the button.
So I think you should see my screen now.
Coming up. Yes, there it is.
Okay, thank you very much. Okay, so I will complement the talk by Harald, showing the status of the T project and the fact that we are now entering in a new phase. So let's start with a little bit of history. So a T is an idea that started many years ago. Me and Harald worked together in from 2004 to 2008 as a co-chair of a working group thinking to what will happen after the current and maybe next future gravitational wave detectors. And the idea of Einstein telescope was generated during that period, and then was let's say crystallized in the next 4 years between 2008 and 2011 with the conceptual design funded by European Commission. and we produced in 2011 the conceptual design report. This document is still one of the main reference documents of the ET project. And then for a list of years, we focus our attention in the existing gravitational wave detectors, but at the same time trying to keep the activity, at least in background for ET, developing the part of the enabling technologies, and also trying to set up as much as possible the environment where to then have the ET project. So in 2020, we had essentially the main step that is changing the face of the ET project. It is changing from a proposal to a status of project. And in fact, we submitted the S3 proposal, and it is a real status changer, and you will see why it's so crucial. And we can say that starting from now, we will have the ET project rather than the ET proposal. So essentially, the submission of the S3 package requested a large activity. We worked for a couple of years, a team of people self-nominated ET steering committee, representing more or less all the scientific communities in Europe working on gravitational waves, terrestrial gravitational wave detectors, and science. And preparing this S3 proposal requested to update our science case, and then you will see from Michele Maggiore what is the status of our science case. Requested the update of the design of the infrastructure to define a timeline, to update a cost evaluation that is crucial, and to evaluate all the other points that are crucial for a so large proposal. So essentially, they evaluate the financial and social impact of such infrastructure, and define who is supporting ET, and realizing a consortium for ET. So the science case, as I told you, you will list more by Michele, and we based the design on the ET conceptual design, the CDR, on the GWIC 3G document, and then everything has been summarized and updated in the document that you see here. And of course, the focus is on ET, on its potential, considering also all the particularities of ET, the triangular shape, the low frequency sensitivity, and so on. The updated design is a new document that you can find also linked in our website, and is a new design for ET that, of course, is based on the conceptual design, but contains a relevant progress that we had to achieve for the S3 proposal. In particular, the progresses are on the science, on the infrastructure, that is the most urgent part of the design that we have to update. And you will see in our organization that there is one board, one team of person devoted in ET to this activity. So Andreas will tell you more in the next talk, and in the session that we will have in the next days. The roadmap is a crucial point, how we develop the activities. We have a very detailed but preliminary roadmap that contains all the tasks as normal for so large project, but I prefer to show this slide that is more pictorial representation, but is telling you what are the main activities that are going on. So people is developing the technology, the enabling technology at this moment, but the main activities are in this moment the site qualification, the iterative evaluation of the cost, are the pre-engineering studies that we are doing as input for the proposal that has been submitted, but now also as an input for the more finalized steps that we leave in the next years. And of course, one of the most crucial activities is the building the T collaboration, and also improving the T consortium that we had to build in order to submit the S3 proposal. So this pictorial representation is telling you all the main steps and all the main decisional points in the T roadmap. So the cost evaluation, I mean, we submitted a preliminary cost evaluation inside the S3 proposal, and it has been updated mainly in the part of the infrastructure, and it has been updated with the support of external companies, large companies that are building large infrastructure like tunnels, motor road, railways, subways, and so on. And you can see that the cost evaluation of the T is in a iterative process. Now we add this S3 evaluation, then we will leave what I call preliminary cost evaluation, because it's based on the design that is in early stage, but is used as input since we have two site candidates, we have two site teams that will customize the design for the two sites, and we will evaluate the cost, and then after the site selection, we will leave a cost finalization. So this is the plan for the T project. You will see in the next slides that the T proposal, the S3 proposal, is a government proposal. The scientists have been essentially a kind of ghost writers, and so for governments it's crucial also to understand what is the social economic impact, what is the return if they investing on that. And so we had a very interesting evaluation by academic economists and by private companies that evaluated the return of an investment on a T. And the return is a factor for the construction phase, a factor 3.6 on total output. You can find here the definition of total output, and something about 1.5 in added value. And so it means that this stimulating the interest of governments in supporting T. And also the operational phase is also something that has been evaluated in terms of socioeconomic impact. We had also to evaluate the services and impact the communities. We worked on the information that are available on Web of Science, trying to depict the links between gravitational waves and all the other kind of science sectors and activities. And it's been a quite interesting study. You can download it still from the website, and also the network of countries, how they are related. So it has been something interesting. Okay, one of the crucial point is that if you wanted to build something of the order of 2 billion, you need to have a very defined infrastructure organization. And so we are working on that. We received as input from the agencies, the main agencies working, supporting a scheme of the project and of the relationship between the collaboration and the project. And in the last weeks, we heavily worked on the definition of the relationship between collaboration and project, in how we needed to structure the project in terms of scientific and technical expertise in order to achieve our target. And a whole session will be devoted Thursday on this point, on the discussion and what it means to enter in the T collaboration, what it means to build the T collaboration. I told you that the ESFRI proposal has been a government proposal, and you can see here the fact that the proposal will be submitted by 5 governments, since ESFRI documents requires a leading country, Italy has been selected as a leading country for the proposal. And so the countries you can see here are Italy, Spain, Belgium, Netherlands, and Poland. They submitted a proposal. When I say submitted a proposal, it means that the ministry write the letter of financial and political engagement for Italy and political engagement for the other countries. So it's a very EV step, a very important step for ET. And but we have also a consortium level. In the ESFRI jargon, consortium is the collection of funding agencies and the universities that signed a consortium agreement document that we prepared as a very light consortium agreement. And we had 41 institutions signing all the consortium agreement at the level of institutions, and this consortium is coordinated by INFN and NICAF, and EGO, the European Gravitational Observatory, the institution that is in this moment managing the Virgo infrastructure, is declared as a headquarter of this proposal. So what is the roadmap in the next future? We accomplished these 2 steps, and we have in front of us the next important steps. So we will be invited to defend our proposal. We will receive a question in February, March, and we will be invited to defend in April, May. So we expect to have a feedback in June and the official decision in September, and a launch of the new roadmap in October, November. And we are really confident to be inside. At the level of ministry delegates and ESFRI delegates, I know that there is a parallel activity going on, and they are discussing together in parallel to the scientist level about ET. So, as I told you, there are sites under evaluations. There are 2 sites. If you read the ET Symposium, the conceptual design, we analyze something like 11, 12 sites in Europe. We now are down to 2 sites under evaluation. One in the border, at the border between Belgium, Netherlands, and Germany, and there are official actions and support from the local governments. You can see here more or less the level of investment that is behind this candidature. Also in Italy, there is Sardinia is a candidate, a site where is existing a mine, where we are doing all the evaluation in terms of noise, geology, and so on. And this site is strongly supported by inside the T project by the Italian governments, and we have already also for this candidature a strong support at the financial level for the evaluation step. Of course, we are defining inside the collaboration the common mode to evaluate and qualify the 2 sites, and there is already official documents available, and we are setting up a team of persons, of scientists, engineers, specialists, the site preparation board that will be devoted to this activity. So going back to the pictorial representation of the roadmap, we will know more about site qualification and pre-engineering studies by the site infrastructure session Tuesday morning and Wednesday morning. We will know more about enabling technology and pre-engineering studies in the instrument science sessions. And we will know more about building the T collaboration and building the T consortium in their organization. And this, I think, it's crucial. It's a crucial session for defining the collaboration. I think should have your complete interest, and I hope it is so, because I mean, as Harald mentioned, we had a very impressive registration to this meeting, with a large participation from all European countries, but not only the European countries. So thanks for your attention.
Thank you, Michele. I think we can take a few questions, although especially I took way too much time. I've got the impression there are none, which gains us a lot of time. So we will then come to the next contribution of this afternoon. That is Michele Maggiore. He will tell us on the science case for the Einstein telescope. Please go ahead, Michele, and share your screen.
Yes.
We can see it.
Perfect. So it's a pleasure to talk the science that we can do with the Einstein telescope with all these people that are interested, with all these participants. So let me start with something that most of you know very well, which is the fact that advanced LIGO and Virgo have really opened a new window on the universe. For decades, we have repeating this sentence that the gravitational wave experiment will open a new window on the universe. It was even boring at some point to repeat this. And now we see that this was really true. Two iconic plots that many of you know, well, many of you have produced and the others know. On the left, the first detection, GW1509, in September 2015. It's already 5 years, more than 5 years. The epoch before by now looks like prehistory from the point of view of gravitational wave science. On the right is GW1708, the first binary neutron star, with the signal from the GRB in coincidence, and then all the multi-messenger study in all band of the electromagnetic spectrum. This has been really the birth of multi-messenger astronomy. Where we are now, Harald already mentioned, this is a very nice plot often shown. These are the black hole detection in O1, O2, and O3A run, compared to the black hole that we already knew from electromagnetic observation, black hole, X-ray binaries of black hole in stars, and neutron star that have been observed by LIGO Virgo. To have an idea of the reach in terms of distance in the universe, the farthest black hole coalescence has been detected in O3 at a redshift of order 0.8, with a certain error, 0.3 of error. So we are already at cosmological distances. And as already mentioned already by Harald, during O3, detection has become a routine, basically one per week, plus neutron star, and neutron star black hole, and so on. So what have we learned? A lot, and let me just give some very quick highlight. From the point of view of astrophysics, for instance, GW1708 solved the long-standing problem of the origin of the short GRB, or at least of some of them. We have understood the neutron star merger are a site for the formation of a heavy element, of the heaviest element through process nucleosynthesis. We have seen that black hole binaries exist, and they merge within the age of the universe. And we have discovered, as you saw from the previous plot, a whole new population of stellar mass black hole, much heavier than thought that we knew through X-ray binaries. Some highlight in cosmology and fundamental physics. We have measured the speed of gravitational wave. It turns out to be the same as the speed of light with 1 part in 10 to the 15. There has been the first measurement of the Hubble constant with gravitational waves, not yet precise enough to resolve the discrepancy that I will briefly mention below, but still they are the first measurement. We have seen, for instance, we start to see black hole quasi-normal mode already from the first event, GW1509, at least the final part of the waveform is consistent with the quasi-normal mode predicted by general relativity. And we started to study, to bound the possible deviation from general relativity. So all this has been exciting, of course, as part, one can say, now already of the history of science. But still, The second generation detector lack the sensitivity to make really stringent tests of fundamental physics and cosmology. So the idea here is that the 2G detector have opened this new window, and with third generation detectors, ground-based like ET and Cosmic Explorer or LISA in space, will start to look deeply into this window. So here I will focus on the science that can be done with ET. For Cosmic Explorer, the situation is quite similar, with some twist here and there. For LISA, it's different. What I will say will be based largely on the document that we prepared for the S3 roadmap that you can find on the archive and that is published, that I coordinated, but with many authors that gave beautiful contributions. And there is also the 3G science book coordinated by Satya, Book, Mandic, which discussed 3G and CA and Cosmic Explorer together in preparation. And more, in fact, I structured my presentation more as an introduction to the theory session that will take place tomorrow at 3 Central European Standard Time. So let me start with this plot, which are so nice that you find a bit everywhere. Also in the talk of Harald, there was this one. So there are the strain sensitivity. So the sensitivity of the detector is a function of the frequency for advanced LIGO. ET in green and Cosmic Explorer pink. And you see that you gain more than an order of magnitude here, and you expand very much toward low frequencies. What does it mean, for instance, in terms of black hole, or binary coalescence? So this is a measure of the sensitivity of a detector. So this is the redshift that you can reach as a function of the total mass of the binary. This is what advanced LIGO can do. For instance, for 100 solar masses as a total mass, you can reach redshift of order 1. What ET and CA, Cosmic Explorer, can do is fantastic. You see that for the best orientation and mass, it could even reach 100, which is incredible. But a redshift like 10, 20 can be reached of a broad range of masses without relying on optimal orientation with respect to the detector. So when you detect black hole binaries up to redshift 20, first of all, you can say, why you care going to redshift 20? There are no stars. Yes, which means that if you find a black hole binary there, it is a primordial black hole, right? So even more interesting. But this means that when you go to this redshift, now we know the rate with some error from the LIGO result, and we expect of order 1 million black hole binaries per year. So understand that this will change completely the game. And neutron star, binary neutron star up to redshift 2, 10 to the 5 per year, possibly a few tenths per year with electromagnetic counterpart, depending on the network of electromagnetic detector that we will have there. Some of them will have huge SNR. So the combination of distances and masses explored, sheer number of detection, and detection with very high SNR has the potential of triggering revolution in astrophysics, cosmology, and fundamental physics, because these are the 3 main directions for the science case of ET. So let me give a very brief summary of the science case organized along these lines. It will be developed a bit later by myself and especially tomorrow. For astrophysics, of course, black hole properties, the origin, stellar or primordial, of course, is a fundamental question. Everything about evolution, demography. For neutron star, you can study the interior structure and do QCD, and study the theory of strong interaction at ultra high density. You can study demography. Of course, multi-messenger astronomy will be another fascinating domain, very rich, both with joint gravitational wave electromagnetic observation and possibly multi-band gravitational wave detection with LISA, neutrinos. Then we can hope to detect new sources like core collapse supernova, isolated neutron stars, stochastic background. In fundamental physics and cosmology, we can start to test the nature of compact objects, study physics really near the black hole horizon, test the existence of exotic compact objects, test GR. We can study dark matter. I will elaborate a little bit on this. ET can study dark matter candidates. Dark energy. We will do cosmology with ET, and one of the most interesting things will be the study of the origin of dark energy. This can be done through the study of the dark energy equation of state, but even more interesting to something that has been understood more recently, which is modified gravitational wave propagation. and the study of stochastic background of cosmological or astrophysical origin. In particular, cosmological origin means a connection with energy physics. But especially, we should not forget that ET will enter into really an unexplored territory and will be a discovery machine. So to some extent, we should also expect the unexpected. So I think, okay, I will go a bit fast here. Astrophysics with binary black holes. As I mentioned, ET will uncover the full population of coalescing stellar black holes, binaries, since really the end of the cosmological dark energies. So we will study, of course, there is a lot of wonderful astrophysics on star formation history, disentangled stellar origin from primordial origin. We also expand very much in mass, as we can detect to cosmological distances black hole with total mass up to a few thousand solar masses. They could be the seed black holes for the supermassive black hole. Some of these subjects will be discussed by Astrid Lambert tomorrow. We can study theory of strong interaction, QCD, with neutron stars. This is a schematic drawing of the interior of a neutron star. When you go inside, we don't know what happens. There could be quark-hadron transition, exotic form of matter. This is a nice picture where we show the temperature in billion of kelvins as a function of the density, which shows that the neutron star, gravitational wave studies of neutron star are highly complementary to nuclear physics experiment, that's it here, and heavy ion collision. Neutron star isolated explore this range here with the same color code that you find here, while neutron star mergers explore higher temperature because of the merger, where you can expect quark-hadron transitions, color superconductivity, many other quark-gluon plasma, many other fascinating aspect of high temperature and high density QCD. This is a well-known and nice plot on what happens from a binary neutron star merger at 100 megaparsec. At the initial LIGO, this is the signal. You could only see the part of the effective point particle. For advanced LIGO, or advanced vehicle, you start to see tidal effect, as indeed we saw. But the real merger phase, which carries the information on the equation of state, on the interior, at a more detailed level, will really be detectable by 3G detector. And Tanya Inderer will elaborate on this in her talk tomorrow. Multi-messenger astronomy. I will go maybe a bit faster because I see I should have some, but no, 20 minutes, right, Michele? So, okay, multi-messenger astronomy. Of course, we can study the formation, evolution, and emission mechanism of binary neutron stars, so kilonova, short GRB. At low redshift, we will have very high signal-to-noise ratio, so we can be able to constrain very well the equation of state both from the progenitors and from the remnant. We will have a golden sample of detection with localization better than 1 square degree, and this will be particularly important for multi-messenger astronomy. At high redshift, we will rather benefit from operating with, say, gamma ray burst detector, like proposed mission like Theseus. We could expect something like 10 coincident detection per year on axis GRB. There will be talk tomorrow by Marika, by Greco, and by Stefan Grimm. This will be more on the triangle versus QL options. But this is the localization as a function of redshift. Also, it's very interesting what ET can do together with 2G detector, binary black holes and binary neutron star. You see that together with 2G detector will be a golden sample of events with localization better than 1 square degree. Marika will elaborate on this tomorrow. From the point of view of fundamental physics and cosmology, again, there is a very rich science case. First of all, we can study the black hole quasi-normal modes. It's a fascinating chapter of general relativity, which goes back to classic work already of the 50s, Reggie Wheeler, Chandrasekhar, Teokolsky. Of course, we are all familiar with the fact that a solid object has its own normal modes, but also a black hole has its own normal mode, quasi-normal mode, to emphasize the decay by emission, gravitational radiation. This is very fascinating. I mean, a black hole is a configuration of space-time, and it has its normal modes, and it radiates its energy in quasi-normal modes. In a sense, this quasi-normal mode represents really the elasticity of space-time in the most extreme regime of strong gravity. GR predict the frequency and damping time as a function of the mass and spin. And this is something that we already started to test and will be tested really with third generation detector, which is particularly interesting because there are several proposals for exotic compact objects that give different predictions in the quasi-normal mode or predict other phenomena like echoes. And Vitor will talk of this tomorrow. Maybe let me skip this and let me move to something a bit more bold. You know, when you construct the science case for something like ET, you should first of all have a very solid science case on standard things in which we are sure that we will give the answer to some fascinating problem. But it's also interesting to be, one can be a bit bold also, and it's also interesting to think to issues, problems that are high risk, high gain. So, for instance, one of the surprises that could be fascinating could be to learn something about quantum gravity. At first sight, this might look a bit preposterous. Quantum gravity is at the Planck scale from particle physics. We are used to this separation of scale. So, how can you learn something about quantum gravity? But in fact, the black holes can act as magnifiers of quantum gravity effect. And a simple example in which already with the back of the envelope computation, you see that there could be something is black hole area quantization, which is a typical things which is, well, from work of Bekenstein and so on, is expected to take place at the quantum level. So the area is assumed to be quantized in unit of the Planck length square. So you can only make transition with a certain quantum of area. And since the area is related to the mass, here I'm writing just for a Schwarzschild black hole in this way, in a transition you have a minimum delta M that you can emit or absorb, so a minimum frequency. When you make this really back of the envelope computation, you find the result like this, and this minimum frequency is of the order of 10 kilohertz for typical solar mass black hole, is parametrically of the same order of the quasi-normal mode frequencies. So if the black hole for quantum effect can emit or absorb only discrete spectrum of frequencies, it could leave an imprint. We elaborated a little bit on this on a recent paper. Maybe Vitor will talk about this. Cosmology, another fascinating direction in which Einstein telescope can give some beautiful results is cosmology and the study of dark energy. First of all, as most of you know, today we have a tension in H0 between late universe cosmology, Planck and DES plus baryon acoustic oscillation, Big Bang nucleosynthesis that predict a low value of H0, and late universe probe like supernovae, which are more quasar, which give a higher value. If you combine this data with this data, and you have a discrepancy of more than 5 sigma, so statistically it's very significant. One might imagine that maybe some systematics, but since now a couple of decades, these discrepancies there, and this group have studied very carefully their systematics, and doesn't seem to get better, it rather get worse. Now, this is a subject in which one typically say, well, this is probably not a problem for 3G detector, will be already solved before. I'm not sure, because first of all, at the electromagnetic level, since 20 years, the systematics have been studied, and I don't expect a miracle on this side. For 2G detectors, from various studies by various people, is estimated that 50 to 100 standard siren with counterpart will be able to measure H0 with sufficient precision, 1%, to discriminate between this result. Of course, after GW 1708 in the Q, with just one neutron star with counterpart, well, we were very optimistic about this, but okay, in O3 there has been no binary neutron star with counterpart, so it's not obvious that we will get very soon to 100 standard siren with counterpart. You can use statistical methods, so-called dark siren, but these are very complicated systematics, and I'm not completely sure that this can be dominated at the 1% level. So apart from this, what you can do is to go beyond for really 3G science. The key relation is the relation between the luminosity distance and the cosmology. And the luminosity distance depends on Hubble parameter and cosmological parameter, in particular the dark energy density. The gravitational wave measure the luminosity distance. You need either an independent determination of the redshift or statistical method.
Metto in...
Sì, Andrea, Paoli, ti stiamo sentendo. At low redshift, this is reduced to the Hubble law, so you just measure the Hubble parameters. This is what a QG detector can do. But when you start to access the redshift of 3G detector, you can start to study the dark energy equation of state. This is typically parameterized in terms of the dark energy equation of state, so that the dark energy density can be written in terms of this quantity. And there are many forecasts for the dark energy equation of state at the Einstein telescope, but I should say that the results are not exciting because we will not probably have a significant improvement on the measurement on W dark energy compared to what we already know from CMB, oscillation supernova, which is that W dark energy is -1 within a few percent. A potentially more interesting observable is modified gravitational wave propagation, which is something we developed largely in my group in the last few years and will be discussed tomorrow by Ennis Belgacem. In short, in the propagation across cosmological distances, gravitational wave amplitude decreases in general relativity as 1 over the scale factor of Friedmann-Robertson-Walker. And this is what gives rise to the fact that the amplitude is 1 over the luminosity distance and why we can measure the luminosity distance. In modified gravity, if you start to touch GR, this result is modified. So that in the end, the amplitude scale in a different way. And this can be a wonderful smoking gun for modified gravity and for studies of dark energy with the Einstein telescope. I will leave this to Ennis tomorrow. Dark matter. It can be surprising that with gravitational wave we can study dark matter. We are more used to study dark matter with particle physics. But in fact, there are several candidates that can be studied by ET, in fact, only by ET or Cosmic Explorer. One is, of course, primordial black holes could represent a fraction of dark matter, most likely, or excluded, or almost excluded. They could make all of the dark matter, but they could be a fraction of dark matter. And of course, it is fantastic for understanding the nature of black hole. If we already have a single detection of a binary black hole at redshift above 10, it's going to be astrophysics. Also, we will explore regional masses like below 1 solar mass, where again, there is no known mechanism in astrophysics that can give rise to black holes. There are many other ways of discriminating between a primordial and a stellar origin. For instance, correlation with large-scale structure. Astrophysical black hole will be correlated with the position of galaxy. Primordial black hole will rather be correlated, if anything, with dark matter halos, and then prediction on mass distribution, spins, and so on. Another interesting candidate for dark matter is an ultralight axion. And depending on the region of masses, this can create clouds around black hole with a mechanism of superradiance and emit a monochromatic signal. So this is another interesting mechanism that was discovered a few years ago, by which you could discover a new particle thanks to gravitational wave observation. Various types of dark matter particles of the type that you can also study, could also imagine to study at accelerators or standard particle physics, could be captured in neutron star, accumulating the core, affect the equation of state in the interior, softening it. They could create halos around the star. So in a binary system, they could make a drag, which you will see with the secular effect. So there are other interesting ways of studying dark matter with this physics. Stochastic backgrounds. Stochastic backgrounds are another way of opening a window on very early universe. The most studied and famous mechanism is the amplification of quantum vacuum fluctuation in the standard slow roll inflation paradigm. This unfortunately is too small even for the Einstein telescope. Is the blue line shown here as a function of frequency. Omega, capital Omega, is the energy density of gravitational wave normalized to the critical density for closing the universe, and the blue line is too small. However, there are many variants on this mechanism that can produce what is called a blue spectrum, a spectrum which increases in frequency. The reason why this is too low for ET is that, of course, there is a free parameter, which is the scale of inflation. And if you raise it enough, you raise this curve, but you cannot raise it too much because at very low frequencies, you hit a bound which comes from CMB. Otherwise, you would have seen gravitational wave in the ratio R that you measure with CMB observation. So there is a limit, and given this limit, and given that the spectrum is flat, in fact, slowly decreasing with frequency, as this frequency is too low. But a spectrum can obey this limit, which is very far away on the left, and still be observable here if it starts growing. I remember several years ago, we started already in the last millennium, we studied these, well, they were studied by Gabriele Veneziano, and then we started with Alessandra Bonanno, Carlo Umberelli, pre-Big Bang model inspired by string theory, give a spectrum of this form. This is another example that we have in our science case paper, in a model in which there is an axiom that interacts with the inflaton. Depending on the parameter of the model, you can have a signal which is detectable. Of course, this would open fantastic window on very early universe physics, but of course they are also speculative. There are also other standard candidates for with cosmic strings. First order phase transition. First order phase transition to give a signal in the early universe, to give a signal in this frequency region should take place at temperature of order 10 to the 7 to 10 to the 10 GeV. Of course, these are energy scale that we will never explore with accelerators, but if we are lucky, we can explore with the gravitational wave experiment. There is much recent work now on the anisotropies and multiple expansion of stochastic backgrounds, both cosmological and astrophysical, and this will be the subject of the talk by Julia tomorrow. I will stop here. I will take a question if there are. Thank you.
Thank you very much, Michele. Are there questions?
I don't see raising the hands.
I think that with 200 people connected, to raise the hand is become is a bit intimidated.
Yeah, I saw that there was also a question on the chat, so you can also write there. And I prefer not to answer in time, but then we will leave time for answering questions to discuss at the end of the full session. We left a few minutes at the end for eventual discussion. So you can write also there, but for sure.
While I show the screen, I cannot see the chat. Yes,
this is Ettore.
Sì, ciao.
Can you hear me? So would you please show the slide where third generation ET is shown together with second generation detector?
Yes. This is a slide on which I guess Marika tomorrow will elaborate. In fact, is her work together with Jan and their PhD student Stefan Grimm. But yes, tell me.
Because I guess we have to survive with this for quite a long period. You know, we're facing a very long future for developing this ET detector. So it is extremely important, really, to define the role that scientifically this network can play. I mean, what is your personal feeling on this?
I think that this plot is very interesting, this plot by Marika, Jan, and Stefan, because it shows that really 2G detectors operating together with the Einstein telescope have a significant role. This is what, of course, I mean, if we will have a configuration of ET plus 2 cosmic explorer.
Yeah, of course.
But this is what, on the left column is ET alone. And on the right is T plus 2G, binary neutron star and binary black hole. So you see ET alone, for instance, binary, just to say, in each bin, it is normalized to the total number of events in that bin. So this upper line is the total detection with respect to the event in the bin. And then you see that ET alone, if you want to have less than 1 square degree, doesn't do much. But already, together with 2G detector, there will be a really significant fraction of event, including event up to 0.2 in redshift, that will have less than 1 square degree of localization. Of course, out of 1 million of events, even if a small fraction has such a localization, this makes a sample of events which is already sufficiently large to take busy all the electromagnetic facilities, given that it will not spend, ELT will not spend all time looking for our signal. So it's very interesting, this plot, I believe.
It is the science we are facing. Thank you.
Any other question?
There is a question in the chat. We could ask that one now. Why is there even a fall off in the sensitivity of telescopes for large total masses? Should the signal be even larger for large masses of emerging bodies?
No, as practitioner of the field, no. At some point you have a cutoff when the mass become too high, because it goes outside the band. For example, already in spiral, the maximum frequency is about 4 kilohertz divided by the total mass of the binary in solar masses. So once the total mass is too large, then the maximum frequency of the signal becomes lower and lower, and in the end it goes out of the boundaries of the detector. So at the beginning, the more is massive the binary, and the more you gain. But at some point, this effect dominates. Otherwise, you would see already supermassive black holes, 10 to the 6 solar masses with 2G. But this is really physical at very low frequencies, as Lisa.
Okay, I don't see any more questions. Thank you very much, Michele. Then let's come to the next presentation from Andreas Preiser on instrument science.
So, share my screen.
Yeah, there it is.
Can you see it full screen as well?
Yep.
Okay, very good. Yes, hello. I would like to come to the other side of the science that we do, the instrument science. And in fact, that will be only the first talk of several locations where you can learn about this. So we have an entire session on Wednesday afternoon where we introduce the body that will do the instrument science work, the instrument science board and its activities. And in that we also have 2 talks for the large prototypes on instrument development. And on Thursday, we have a session where we rather have just individuals presenting research and development from the area of instrument science. So please come along to those. What I would like to do today is just introduce the instrument and the design that we're having. So some of you have seen this many times before, but I think there will be enough people for whom this is new. So from the picture, we can already see what ET will be. That is an underground site. It is a triangle. It has 10-kilometer long underground tunnels. And the experts know that inside we have vacuum systems with laser interferometers, with super polished optics. That is similar to the current detectors. So let's go a little bit more into detail. But if you want to know all the details, we have a lot of documentation that you can read. In 2011, we made the conceptual design study for ET, and we recently updated this for the purpose of the S3 application that Michele was talking about. And you can find this on the link provided here. So what has changed in the document? When we did the update of the design, we made a decision to try to limit the number of changes. In particular, we would like to keep the same sensitivity curve which had been used to compute a lot of the data that you've seen in the science case. So the task was to just clean the design in a sense of bringing it up to date with the state of the art of the instrument, and also remove options. In the original document, we had a lot of alternatives. The new document provides one baseline design. And some of the details that we did change. So we worked, as Michele said, with companies on infrastructure, and that led to some changes in that area. For example, we moved away from these very large caverns at the corner of the triangle, and now you will see later on we have several smaller ones. Part of that, we wanted to shrink the tunnel or make more space for the main optics in the tunnel, and we did this by removing the filter cavities and our auxiliary tunnels. So this is more for experts that know what I'm talking about. You will see a bit more basic information later. Yeah, then Another two changes are use of beam expander telescopes in between the beam splitter and input test mass. That is something new in the field. And we used to have higher order Gaussian modes at the beam for the high frequency detector. These have been removed because we can achieve the same thermal noise target by assuming A+ like coatings. Okay, but now back to the basics. So ET is a triangle. The triangle is actually just a shape composed of having 3 detectors in one. So each normally gravitational wave detectors is L-shaped, and here we fold them a little bit more into a V, and then we can have 3 in one triangle. That is meant to be the near optimal configuration for having a single site and having it cost efficient, meaning you have 3 detectors, but you only need to provide 3 corner caverns, and you can use the tunnels multiple times. And that is interesting because the triangle then can provide or be equivalent to other configurations. So namely on the left, it could be if you just sum the signals of these 3 interferometers could be equivalent to having 2 interferometers orientated like shown in the left diagram. That would be optimal for both gravitational wave polarizations at the same time. Or if you sum up the signals slightly differently, then you can have it equivalent to the topology shown on the right, which is where you have co-aligned detectors. And these allow a couple of things. So first of all, they allow using null streams that are techniques to better distinguish signal from noise, and I'll show you a bit more later. But also they're just showing redundant interferometers. So you can, for example, upgrade one while the other one is running. And last but not least, the triangle provides this in a single site, which I said should be cost efficient, but it gives you also a prominent design. Here's one example I would like to show on the effect of null streams. One of the challenges that we have is as we all increase the signal to noise ratio in future detectors, our performance on extracting the parameters of the sources might not be limited by our signal to noise, but our calibration accuracy. So on the top right, you see a plot of the current calibration accuracy in LIGO-Hanford, and there's the link to the very elaborate paper on this. And you see it varies between a few percent in the best region to 10% in the worst. And in ET, we need sub 1% calibration accuracy. And a recent paper here describes very nicely how a null stream can provide that. And ET, by having local co-aligned detectors, can do that in a way that is independent of the sky position and the polarization of the source. So the triangle is one of the outstanding features of ET. The other outstanding feature is low frequency performance. So you've seen this plot before. If you compare ET to the Cosmic Explorer, the other 3rd generation detector currently being designed, you see this relatively small change here on the left that the ET curve pushes a little bit to lower frequencies. So that looks very small on this plot, but it has significant impact on both the science case and also on the technical design. I don't want to go much into science, but this is one plot that we all like and show very often, done by Evan Hall, where you see the time to coalescence for binary neutron star for different detectors. And on the y-axis is the signal to noise ratio, and we pick an arbitrary line of 8 and then see when we could detect this. And you see with ET, we could give early warnings to astronomers 3 hours before coalescence. So that's one of the benefits of having the low frequency performance. And the way we do it, as Harald has explained briefly, is that we decided to split each detector into 2 interferometers. And that allows us to optimize them individually for high and low frequencies. The high frequency one is an extension of the state of the art that we have. So it's similar to advanced LIGO and Virgo, but running at higher laser power. And the low frequency detector instead, where we can optimize the laser power and the quantum noise scheme in a different parameter space, so that it's better for low frequencies. But it also requires and allows us to implement new technologies. You see here at the lower plot the limiting noise curves in the low frequency are the seismic noise, the gravity gradient noise, and the suspension thermal noise. So that immediately leads you to these ideas that you've already heard, that we're going underground to limit the gravity gradient noise, and to go cryogenic to limit the suspension thermal noise. So here are a few more graphics on this idea. So we call this split into two-tone interferometers, the xylophone design. And as I said before, in the triangle, we have 3 detectors. Now, each detector is composed of 2 interferometers. So we have 6 interferometers in total. And on the lower right, you see simplified layout for these interferometers, where the high frequency detectors on the right with room temperature optics, a normal wavelengths in our field of 1 micrometer. And it's a very similar optical layout. And on the left is the low frequency one, where you see some differences. Some of the mirrors are cryogenic and a different material. We use a different laser wavelength, and we have slightly different optimized quantum readout. In the parameter list on the left, you see the full set of design parameters. They don't really show the full story, what is complicated. I just wanted to highlight a few differences here. What I circled, or not circled, but where there's a red border, you can see the different light powers. The input power and the arm power are obviously related, but you can see that what I mentioned before, ETHF is using high input power for high arm power, and that's going a little bit beyond what we have now. Whereas ET low frequencies can use lower power, and that is the optimization you can do for the quantum readout. Then the orange borders show 2 areas where there's really much behind these numbers, and I would call it new technology. The top box describes that we go to cryogenic mirrors with a different material and very large size masses and use a different wavelength. So this is new in our field. Even though we have started in this direction, there's a lot more R&D needed. Then on the lower part, there is another box which highlights the seismic isolation system. This is again a bit for insiders, but this is a structure I'll show you later, which is more than just a number. It's a very large research and development program. In the next few slides, I'll give you a few examples. You will see much more of these in the Wednesday session. So let's start with the optics. As I said before, we have 2 interferometers and we have different materials. Both of these interferometers need larger scale masses. So we go from typically 40 kilogram masses for the mirrors, for the main test masses, like we have now, to something like 200. That is a challenge for even just producing the glass at this size with the right homogeneity, purity, optical and mechanical qualities. It has been a challenge in initial detectors until we got to the state where we are now. And now we have to pursue this at a new level. And in addition, we need to improve the optical coatings. That is an ongoing challenge, even for the current detectors. So there has been a lot of work and success in recent years. And here below I've shown 2 examples why we think we're optimistic that we're on the right track. But this is not the end of the story yet. Then for the seismic isolation that I mentioned before, that is a system that decouples the test mass from the ground vibrations. The design is based on the successful design that is used in the Virgo detector that is shown on the left. So that is actually a Virgo design here. And the ET designs are using the same technologies and are upscaled. Of course, the high frequency detector can use these in a very similar form. But for the low frequency detector, where we have to incorporate cryogenic cooling of the mirror, we have a lot of work to do. And on the right picture, it just highlights a few of the questions that need to be answered in the development of the cooling system. It can come from very mundane questions like what kind of pumping we have to do, but also to quite complicated combinations of how can we extract the heat from the mirror, what cooling technique is low noise enough for vibration isolation, and so on. Again, as I said, that is a big topic, and you see more in the Wednesday session. And one thing I would like to highlight is the need to have a slightly different focus to make ETH successful. So in the activities, we highlight in an entire strand of our activity what we call active noise mitigation, which is something that we haven't had in the same form in current gravitational wave detectors. And the reason is that we really go beyond a small improvement when it comes to low frequencies. Over the wide frequency band, we improve between current detectors and ET roughly by a factor of 10. But if you look at, for example, 3 Hertz, the improvement that we aim for is between 200,000 and 7 million. And that's a game changer, but it also requires a complete rethinking of how to reach this low noise at these frequencies. Here is depicted the problem in terms of seismic activities. So you have to also lower your susceptibility to the entire spectrum, which includes small earthquakes, the microseismic peak, and an area where we typically have resonances of our mechanical structures. So that's is another research program that is quite broad and needs a dedicated focus. It is connected to sensing. So if we want to reduce our susceptibility to seismic noise, we need to measure it much better. And one of the troubles we have is coupling between the horizontal motion, tilt motion in seismic sensors, and there are various research programs on the way. With just here a couple of pictures and examples of ongoing research programs. I don't want to go into them into detail, but they all follow the idea that we make the platforms from which the individual mirrors are suspended quieter in a sense of inertial control at low frequencies. And that will allow us to decouple the optics from aggressive control system and so achieve lower noise. And it will also hopefully allow a shortening of the suspension chains. The other thing that we do for reaching a low noise environment is to actually go underground. So if you look at seismic noise, on the surface, you have a much higher amplitude of seismic noise. So the lower you go, the lower your seismic noise. If you look at our noise plots, it's actually not the seismic noise we're worried about, but what's called Newtonian noise, which is the direct gravitational coupling from masses that move driven by typically seismic noise. And here on the left, you see some estimated plots where for different depth, you see the coupling of the seismic noise from body waves. And you see the lower you go, the lower this coupling becomes, but you can also see it might remain critical. So if needed, we would want to apply cancellation of Newtonian noise. That could be done with using areas of seismometers, and that's an active area of research. In the middle, you see another type of Newtonian noise coupling that comes from atmospheric movement of masses, or air movement. And here, the cancellation, active cancellation, is deemed to be very difficult because we don't have good monitoring tools, unlike with the seismometers. But here, luckily, by underground, you can see that we achieve or hope to achieve a natural reduction of this effect below the sensitivity curve. And then the big challenge for us is that we have to create an environment that actually retains the low noise performance underground. And here on the right, there are two noise curves showing this kind of noise that you create yourself. The top line is for the Virgo interferometer, and the green line is for Kaga, the Japanese detector. The good news is in the low frequency band where we're most worried, the Kaga environment, even after installing all the machines and running it, seems very quiet. But you see in the higher frequency band that Kaga generates a lot of self-environmental noise that we would need to address by designing the underground infrastructure better. Talking about noise, for the experts in the field, we all use a tool that's used to be called GWINC and now PyGWINC, that is maintained by our LIGO colleagues, that allows very easy use of noise models to compare designs, to predict sensitivity curves. In particular, it's very useful to make sensitivity curves that can then be used in mock data challenges. So we have this design curve from 2011, and now after we have updated the parameters for the new design, where I said we wanted to have minimal changes, but some changes were necessary. So we see a few details popping up, but very few. So here plotted on the right, an example for the high frequency detector curve where there were the most changes. So we changed a couple of things here: the length of the filter cavity, the type of laser beam that's used, the length of the recycling cavity. And what is actually shown here is only one change, which is related to the last point, a longer signal recycling cavity, which makes the sensitivity curve deviate slightly at high frequencies, but not in a way that is that we worry about right now. Okay, now bringing this all together, it makes a complicated detector, as you can imagine. Here, this is more for offline consumption. I think I tried to show you how one corner of the triangle would look like, where a few things come together here. So remember, we have in each corner of the triangle one detector, which consists of two interferometers. So you should find two interferometers here, but you should also see the end of the other detector that was in the other corner of the triangle. And let me just go briefly through this. So coming from the right, we see actually the end test masses of the detector from the other corner. First, the high frequency detector end test mass, then the low frequency detector end test mass and its output optics. And then from here on the left side, you see the beginning of the arms for the detector that has the center in this corner. Again, there are two, then high frequency and low frequency. What you can't see so easily here is that they're sitting on top of each other. So to view this a bit better, here on the bottom, you see a side view of the tube. So there's a tunnel with the tubes. So you see here that the tubes inside the tunnel are stacked, and the color code shows you that the high frequency vacuum is always on top and the low frequency vacuum is on the bottom. And in places where we have a cryogenic shield, that is shown in blue. And then on the left in the central cavern, you have what we call the central interferometer and the input-output optics. So as a central beam splitter with the input and output system. So here's a laser with mode cleaners, use a filter cavity and the main detection bench. You see also there's a second cavern on the top, which is the same as here with the beam splitter and input-output optics, but for the high frequency detector. So this is a slightly complicated layout, as I said, a little bit for offline consumption, but let me spend my last few minutes, give you a little bit of a slideshow to make that a bit more realistic. So here you see an effort we've undertaken to show that design in 3D, which we found very important and impactful for the infrastructure design and also for things like the vacuum system. In 3D, you can easily spot when things are colliding and spot mistakes that in a simple 2D layout you wouldn't be able to see. So this shows the full triangle. Please note that the tunnel length here is not to scale. So this tunnel in the middle is 10 kilometers long, while the structures are hundreds of meters long. The key here is that each corner of the triangle is an identical structure. So we can zoom into one of these corners to see what's there. And here you see the same diagram that I've shown you before, but as a 3D structure. We again have the long tunnels here coming from the right. We start with the end test masses of the other interferometer, and here we have the input test mass of the high frequency detector. High frequency is here always shown in red. Here's the high frequency beam splitter and its separate cavern. And on the left, there's the large cavern with the main beam splitter for the low frequency and its input-output optics. And we have here kind of shown also auxiliary tunnels. That these darker ones are construction tunnels that are needed during the excavation. And we have an access tunnel to the left. Now, to go a little bit more inside, to get a visual feeling here, I'll show you a few pictures. Again, this is the same as before. The long 10-kilometer tunnel comes from the upper right, and we're hitting here one corner station. Here we can't see the end test masses of the other detectors. They are physically separated by a large distance so that the noise between this detector and the other detector is not correlated. And you see here the end test mass, the input test mass for one of the arms, and then followed by a so-called beam expander telescope. I'll show you more in the next picture. And you see here something similar for the low frequency detector. And on the bottom here, for example, would be the filter cavity pipes going into the tunnel towards me. And one of these many vacuum towers here in the middle is the low frequency main beam splitter. So typically all of these large structures host either one optic at the bottom, if it's a main optic, or a little bench which can host several smaller optics. So going a bit more closer, so that was in the upper right corner before. Here's what I meant before, the input test mass of this particular arm. Then the beam goes through a telescope and then goes through this other tunnel to the extra cavern for the main beam splitter for the ETHF interferometer. And you can see nicely here how the low frequency interferometer beam is just passing below this entire optics for the HF interferometer. And here one picture like this again, just a slightly different view again. What I want to show here is that upper right, that's what we've seen before. The next structure here hosts the input test mass for the low frequency detector, and that one is the cryogenic mirror. So you see before and afterwards, we have about 40-meter cryo shield. So the cooling is not just the mirror here, but we have to cool a large stretch of the tube to avoid radiative heat transfer with a warm environment. And then from here on, the optics are, again, room temperature, even for the low frequency detector. We start here with the beam expander telescope and then go here to the main beam split. So I hope that gave you just a visual kind of impression of how this all comes together at the top. What is also similar here in this design to the Virgo design is that the access to the optics to install it or to clean it would be from clean rooms located on a lower level below the structure that I've shown you before. And yeah, finally, just for completeness, this is the other cavern where you have the central beam splitter for the HF detector. And here, because it's a bit more close up, you can see the scale of the system. And you can also see how the different vacuum structures have different sizes. And that comes just from the fact of different requirements for the vibration isolation systems that are located inside. Yeah, and with that slideshow, I just want to end the summary briefly as a bit of my personal opinion. So the Einstein telescope will be a high-tech laboratory, and it will be driving new technologies that go beyond the state of the art. What we're planning here is really a long-term infrastructure with a prominent and unique design. The instrument inside the structure is based on existing technology. So we're scaling the state of the art. We're not reinventing the wheel, but we start with the best systems we know. But for the low frequency detector, we have to add a specific number of new technologies that we have to develop. And the scaling of what we have now already is a challenge for research and development. And in particular, the new technologies require new development programs. And in particular on those, you will hear more in the Wednesday and Thursday sessions. Yeah, thank you very much.
Thank you very much, Andreas. I see that there is one question already in the chat. What is the reason or the advantage for using a Virgo-style suspension compared to LIGO-style suspension? That's the question.
Yeah, they have both disadvantages and advantages. I mean, partly here we use the Virgo system because it has already proven lower frequency performance. So I'm not an expert in suspension, so please take it from a relative informal guess here. For me, the difference is that the LIGO suspensions strongly couple the internal modes, which makes it easy to damp them quickly, but it's not so easy to get them to a low noise performance, whereas the Virgo suspension design has a different approach, which is decoupled modes, which means they're hard to damp if they get excited, but they provide better passive systems at low frequencies naturally.
Any other question?
Maybe I can add one word about that. There is a publication by Braccini et al. That has been made during the design, conceptual design phase that proven the fact that down to, if I remember well, 2 Hertz, with the right scaling of the Virgo suspension, you can match the sensitivity curve. But this doesn't mean that the design of the detector is frozen. As Andreas said, we are having a very conservative approach. So we are basing the design of the detector where it is possible on proven technology. And then, of course, it will evolve because maybe you said, Andreas, but it's important to stress the concept that it will be mainly a research infrastructure. So this means that we lost the third generation detector and all its evolutions. So for us, it's quite important to design an infrastructure that is not limiting the sensitivity of ET and the future evolution of ET.
Okay, I don't see any other hands up or questions in the chat. Thank you again, Andreas. And then we come to the last talk in this session. Sorry?
Thank you.
Oh, okay. Then we come to the last talk in the session, given by a guest from the other side of the Atlantic Ocean, Matt Evans from MIT, talking about the other 3G concept, Cosmic Explorer. Please, Matt, go ahead.
Everybody, is my microphone working all right?
Yes, everything perfect.
Great. I'm going to pop up the participant windows in the chat. I'm not sure if I'll pay good attention, but if I see something come up, I'll try to answer questions. Hopefully, I will be able to make up some time here because it looks like I know the things that I was going to talk about have already been presented. So we might be able to get back on schedule. So I will be talking about Cosmic Explorer, which is a concept for a 3G detector developed in the US. And we've seen the Einstein telescope picture here, which I obviously stole from Michele. I wanted to just highlight some things that have been mentioned already. This is, of course, all this is obvious to people who have seen these things a million times, but I guess there are some new people in the audience here. So I would characterize ET as having a few main features which are different from Cosmic Explorer. The length at 10 kilometers, the notion that it's necessarily underground, having these 6 interferometers, is a sort of unique ET feature, and the plan is to operate the low frequency detector cryogenically, by which I mean something like 20 Kelvin, so actual cryogenics. The Cosmic Explorer plan is rather different from that. CE is intended to be a larger, so 40 kilometer L-shaped detector, more similar to the current generation of detectors. On the surface, single interferometer in a facility, and we might be operating. We'll start out operating at room temperature, and future evolution may be cold, but not. So by cold, I mean silicon and 120 Kelvin, or it may remain at room temperature. So we're not planning on any real cryogenics for Cosmic Explorer. I think those are sort of the top level conceptual differences between CE and ET. The very rough and funding dependent timeline for Cosmic Explorer looks like this. This was published for the Astrodecadal in conjunction with the LIGO Lab. Our timeline says that right now we're working on R&D phases, and we're hoping for construction to begin in the early 2030s, and observations would be in the latter half of the 2030s. And we have CE evolution broken up into two phases. So there's a stage one where we're using essentially just scaled up current technology. There's some R&D to be done for stage one, but we try to keep it as limited as possible. And the stage two of Cosmic Explorer is sort of a farther down the road detector, which involves some technologies which are really not ready now. We don't envision them being mature in the next decade at a level that we would be comfortable installing them. So this is where we might be going to a lower temperature, using a different wavelength of lasers. That'd be 2 microns instead of 1 micron, possibly silicon optics. So there's still some open questions about what to do for CE2. And we pushed that to the 2040s as the likely time for installing this upgrade to the detector. And this is similar to the way LIGO has operated with the initial LIGO phase using, let's say, conventional technology. At the time, it wasn't proven, but relatively easy stuff. And then the advanced LIGO phase was using what was at the time sort of new and unknown technology, which now has become commonplace. So that's the idea for Cosmic Explorer, sort of two-stage approach. And you'll see me refer to these in the following slides as CE1 and CE2. So what we've been doing since the last ET Symposium is really working on defining what are our science targets, our sort of key science outcomes for Cosmic Explorer, and performing a detailed trade study on what we could change about the design of Cosmic Explorer and how it impacts the science that we can do. So we've picked our science goals. We've tried to look at what else will be out there in the scientific landscape in the 2030s and 2040s, and find something that's unique to Cosmic Explorer, or at least unique to gravitational waves for our science targets. And then we're optimizing the CE design to try to follow those science targets. We've been, in conjunction with that, updating the technical design for Cosmic Explorer and really just sort of fleshing out a lot of the details. And there have been thoughts about how we'll do data management, how we're going to do computing for Cosmic Explorer. So starting to get into the, so let's say, computing side of it, not just the instrument side or the astro side. We've been talking to civil engineers. And much like for ET, as you start to talk to people who build things, you discover that some of the physicists' ideas of how things would go are not really how things work. So we're getting to some more of the details there in terms of the civil engineering for Cosmic Explorer. And that's really targeted at producing a fairly accurate cost estimate that we can then move forward with. And we've been trying to build the community. I'll talk more about this as we go along. So the key science outcomes we have chosen are shown in this donut plot. We seem to like these donut plots. This one was made by Satya and company. And we have three main areas that we're focusing on. So I'll start with the blue one, and that's extreme gravity and fundamental physics. So a lot of these things overlap with ET. I'm not going to go into detail on any of these. But rather than having a sort of more lengthy list of targets, we really wanted to have just a small set, three, and then within these three science targets, we pick out some highlights of what we're looking for. So the orange section, black holes and neutron stars through cosmic time, is again, this is really an expression of the fact that Cosmic Explorer, and really hence the name of Cosmic Explorer, will be able to detect essentially all of the compact binaries in the universe when you get to CE2. And this lets us explore both the black hole and the neutron star population back through the peak of star formation at redshift of a few, and in fact out to a Z of about 10, where you don't really expect these sources to exist until you start talking about things like primordial black holes. And the bottom of this is the green section, and this is dynamics of dense matter and extreme environments. So here we're thinking of neutron stars and what we can learn about nuclear matter. So we've put this together. We talked about it in the recent CE workshop, and we're starting to incorporate feedback we got from the community there. I think mostly we're on target, but we also got some good input on that. We've already seen these noise curves. The only thing that I'll highlight here that Harold didn't already say is just sort of this distinction between CE1 and CE2. So the progression we expect from using essentially current technology in this large facility, so scale up current technology, to CE2, which is somewhat more speculative, is this factor of not even 2 in sensitivity here. That might not seem like a lot, but the cost should be incremental compared to the cost of the facility, so it ends up being a sort of a no-brainer as a thing to do if the technology is available. I'll also point out the high frequency end of this, where ET and CE are overlapping fairly well here, and I'll just want to point out where this is because I'll talk a little bit more about this later on. If you put this into the redshift at which we can detect a variety of sources, this is why we talk about black holes and neutron stars throughout cosmic time. Because we're getting to detect systems over a very wide mass range. So the x-axis here is the total source frame mass of our system. So from a total mass of a few solar masses out to total mass of a few hundred solar masses, we should be able to detect, or at least have some chance of detecting a source out to a redshift of 10. So this is the horizon, so we won't detect everything here, but things in this region will have a chance of detecting. There are many sources expected at redshifts of a few. When I say many, I'm talking about hundreds of thousands to millions per year should be detectable. So we should have a lot of sources here. This donut plot was made by Evan Hall in conjunction with Salvatore Vitale. And it doesn't have as much information as the previous plot because it picked out a couple of fiducial masses in order to make this sort of graphic. So I'd say it's more visually appealing, but less information in it. What it does show is where we expect the populations of neutron stars in yellow on the left here to be, and where we expect the populations of black holes to be. Mainly, the message is that we expect them around the peak of star formation at redshift of a few to be the majority of the population. It also shows how far we've gotten into sampling these populations so far. NEMO is on here. For this one, we don't need to worry about NEMO. We have Advanced Virgo and A+, which will come in the middle of the black hole population, but still very far from the peak of the bioneutron star population. The Voyager detector in orange here, I won't really talk about it, but represents the best we think we can do in a LIGO facility. And with that, we can get most of the black holes, but still not all of the neutron stars. You see, as we progress to third generation detectors, we have a horizon which is well beyond where we expect to find astrophysical black holes. And for neutron stars, until you get to CE2, you're not really seeing the whole population, but you get a good sample with CE1 and ET. For our science goal of extreme gravity and fundamental physics, I think there's there are two short messages that can be associated with this. So here we're looking at sources. Here I've put this green arrow. So some tens to about 100 solar masses, total source frame mass, and they can be out to high redshift for these things. But the ones which are close by, so somewhere in here, we should have an SNR which is very large, so order 1,000 for these kinds of systems. And with that, we expect you to do precision tests of gravity, precision tests of GR, or whatever your favorite alternate theory is. The other thing is with thousands of these events per day, we also expect to be able to cherry pick the most interesting events. So there will be events which are particularly revealing in terms of the physics behind them, things with high spins or large kicks, edge-on systems, high ellipticity systems. There'll be things, sort of the oddballs, which could tell us a lot about physics. We'll have a lot of events to choose from, so there should be more oddballs. So our second science goal of dense matter and extreme environments really comes from bi-neutron star mergers. And here I put an arrow where we expect them to be found again at CE2. That's out to very high redshift where we don't expect to find any. Again, what this means is for the things which are close by, the SNR should be very high. And in particular, we're looking at the SNR at the high frequency region for these. The thing we're exploring there is not just the equation of state, but really we get more into the QCD associated with this phase diagram of quarks and gluons. And depending on whether you're looking at the tidal phase or the merger phase, you're a different part in the temperature part of this plot. So there we're doing some, let's say, fundamental physics, but really nuclear physics. Okay, so that's all I have to say really directly about the science case. Similar to ET, I think we've tried to keep the list short in terms of things we're going to work on. A few things have changed for people who've been watching the evolution of Cosmic Explorer, so I want to just highlight those changes. The first has to do with how we envision the technology for CE2, and what we've discovered, and this is mostly work by Evan Hall and Kevin Coons, is that the low frequency end, this is a noise budget like the one shown by Harold, it gets complicated at low frequencies. And the message I'd want you to take away from this is that this one is our nominal CE2 design, which is operating as a 2-micron laser at 120 Kelvin, silicon optics, sort of all new technology. And over here, we're comparing that with CE2, which is made using 1 micron, more or less conventional technology, but really pushing the boundaries more than we would with CE1. And what you can see is that these two things are essentially identical. So what we have here is really two paths that we could follow to get to the CE2 target sensitivity. And we're not prepared to choose right now which one of these two paths will follow. They both have potential problems and sort of open questions associated with them. That's what CE2 is for, is a place to put things where we're not really sure how we're going to do it. But at the same time, I would say it's good to have more than one way of getting to your goals. I talked a bit about the trade study, and one of the things that's coming out of the trade study is it's becoming clear that what we'd really like to have for Cosmic Explorer is both a 40-kilometer and a 20-kilometer instrument. And I say that because they both have certain advantages. The ideal network would be a combination of the two. And the trade study is really getting into this by looking at hundreds of different potential future networks and different designs for Cosmic Explorer, so 10 or 20 or 30 or 40 kilometers in length, and different tunings for the optical setups to try to discover what's the best way for us to put together a network. We're not done with this just yet, but it looks like the output is not just a single 40-kilometer detector, and not really even that a 40 kilometers is necessarily better. To explore that a little bit more, if we're looking at our science goal of the dynamics of dense matter, the thing that we see is that we can change the sensitivity curve of Cosmic Explorer, if we construct the signal extraction or signal recycling cavity carefully, it can be made such that we can really tune the response of the interferometer by changing the reflectivity of the signal recycling mirror. So a relatively easy mirror change, not involving detuning, can allow us to move from a sensitivity curve which is optimized for compact binaries to something which is optimized for extracting a high frequency post-merger signal. I pointed earlier to the high frequency region of this where CE and ET were overlapping, and the curves that are used in that standard plot are something like this dashed blue curve here. And it's rolling up in a region where we might want to detect post-merger signals, so 2 to 3 kilohertz, which would tell us about sort of the warm QCD phase diagram. And it's rolling up here in a way that is sort of cutting off the sensitivity that, in a region that might be of interest. And what we can do to fix that is to try to tune the detector to have a dip in the response, so low noise in that particular region that we're looking for a signal. We call this a post-merger optimized configuration, as opposed to the dashed ones, which are the compact binary optimized configurations. They're just looking to have a high signal to noise ratio in the in-spiral phase of in-spiral and say, late in-spiral phase of black hole systems and neutron star systems as well. The reason why we're considering both 20 and 40 kilometer instruments as interesting is that the 40 kilometer instrument, if you say, I want to optimize for compact binaries or optimize for post-merger signals, it doesn't change very much in here. And that's because the length of the detector is such that the light round trip time in the arm, known as the free spectral range, makes it very difficult to access this 2 to 3 kilohertz region. If you make the detector a bit shorter, so I jump to the 20 kilometer curve in green here, you see that you can put a dip very nicely in that region by changing the signal recycling mirror. And that allows you to improve the sensitivity there, where, as you saw in the earlier plot, CE and ET are similar. That can be improved by roughly a factor of 2. At somewhat higher frequencies at 3 kilohertz, even by as much as a factor of 5. So you can make a large increase in the sensitivity in that post-merger region, which could be interesting for learning about dynamics of dense matter. I mentioned in here that 30 kilometers is not a good compromise, and that's because it's sort of worse in both configurations. It's not short enough to allow you to really gain at a few kilohertz, and you're losing in the compact binary optimization at low frequencies. So we feel like 20 is good for post-merger, 40 is good for compact binary signals. And that's why we would ideally like to have one of each. Okay, so then before I wrap up, I want to talk a little bit about the near future. So this end of the timeline over here. And for the near future, what we're doing right now, the Cosmic Explorer team, and this is a 5-institution collaboration, the institutions listed here, we'll be finishing up our current project, which is to write the CE Horizon study. This is something which is similar to the, let's say, the ET book plus update. We're going directly to the update because we're a bit closer in the timeline to when we hope to start building. But so that's our current project. We'll be wrapping that up next summer. We've also created the CE Consortium that happened recently, and we have now several hundred people who have joined as members. All are welcome to the CE Consortium. There's no problem with being both an ET and a CE member. We really have this consortium there as just a way for people to keep track of what's happening in Cosmic Explorer and a place where they can talk about research. So anyone can talk at the various research calls that happen here for Cosmic Explorer. So we can keep people involved and keep track of everything that's happening. The next big step for Cosmic Explorer, we expect to be a conceptual design phase. And this I put in quotes because it's something that's defined as a particular meaning for the National Science Foundation in the US with respect to the large scale projects. And this will be some tens of millions of dollars. We'll then have a project office and they're sort of on the rails at that point to construction. That won't happen until we have some, let's say, blue ribbon or high level study happens, which gives us the thumbs up. This is what we want to do. And we also need to have a, let's say, broad community agreement that we're going in the right direction. In the meantime, we're expecting to have individual PI grants supporting R&D relevant to Cosmic Explorer, and this will be coordinated through the CE Consortium. So these will be both on the science case side in terms of deepening our understanding there, and on the instrument side, and really paving the way for a next generation detector. Again, the consortium members are all encouraged to participate in this. So this is not something where we expect these 5 institutions to be doing all the work for the next couple of years. We're really hoping to have everyone in the consortium participating in the R&D efforts. All right, so I'll wrap it up there with the message. The next few years, we're going to be continuing to develop the science case. So for the next year, we'll be finishing up the Horizon study. Once that's done, papers will continue to be published about the science case, and we'll develop that farther. We'll be trying to tick off the boxes for CE1 research for scaling things up, and continuing development on CE2 technology. And I just want to highlight again that there's a lot of work to be done and a lot of development here. And we'd really like to encourage everyone to participate. So here's the link to the Cosmic Explorer Consortium. You can probably even remember it, just cosmicexplorer.org. From there, you'll find the consortium link. All right, so that's what I've got. Thank you, everybody.
Thank you very much, Matt. Other questions?
Take questions if anyone likes.
Yeah.
What's the model that you foresee to access to CE data? Map is asking.
Yeah, right. So the current idea is that we're hoping for, let's say, almost real-time open access. And we're trying to figure out how to do that. But the idea would be that we produce real-time data and some metadata about events in near real time, so as quickly as we can. And then subsequently, there'll be some analysis done within CE, but we'll expect most of the analysis of the data to be done by the community. So that's our nominal computing model. And the CE project is not planning on having the majority of the computing done within the project.
I have a question for Matt. Something that I haven't understood. The option 20 versus 40 is building 2 different detectors co-located, 2 different detectors located in different places. I haven't understood this point.
Yeah, excellent question. So I should have been clear about that. What we would like ideally is to have 2 detectors like the LIGO configuration, which are not co-located, and one of them would be 40 kilometers and the other would be 20 kilometers. There's a few ways that we can envision this happening. One would be a 40-kilometer instrument somewhere in the US. We have some sites we're looking at, and another one somewhere else. So like LIGO, you sort of split them as best you can across the US. And the sites that allow for a detector of this size tend to be sort of from Texas west in the US. It's hard to find things towards the East Coast that will allow for a large detector, but we can still try to make as long a baseline as possible there. And of course, we would, in this case, aim for 2 detectors which are sampling 2 different gravitational wave polarizations, as opposed to the LIGO configuration in which the detectors were as aligned as possible. And that's the difference between a detection machine, which is what LIGO was built to be, and something which is really targeting a particular science where you want to have both polarizations and you expect high SNR, so it's not so important that you have exactly the same signal. Let me also put in there that we're working with the folks in OSGRAV and making plans as well for CE South. So the ideal situation would be 2 detectors in the US and 1 in Australia. One could imagine a different future in which there's 1 detector in the US, say a 40-kilometer detector, and a 20-kilometer detector in Australia. So there's more than one way to get 2 CEs online.
Okay, I don't see any other questions. Oh, there is one. Let's see. Having an increased sensitivity, and as it was said that almost 10 to the 6 events per year might be seen, wouldn't it get very tricky to disentangle events from all this background?
Yeah, so I'm not really the best person to answer this question, but I'll give you the short answer that I know as an instrument scientist. For the black holes, I think it's not so tricky, especially for Cosmic Explorer, because the events are in band for a bit shorter time than an ET. But the events are separated by 15 minutes roughly, and we don't know these things to great precision. So it could be 5 minutes, it could be 35 minutes. It's not like we have that level of precision, but we expect that relative to the length of the high SNR portion of the signal at the end, which is order a second or less, they're distinct. So they're much more like popcorn than like white noise. For the bineutron stars, that's less true. And in fact, there are a number of people putting in a proposal now to do a mock data challenge and try to see how far we can dig into the bineutron star signals before we hit some kind of confusion limit there. I don't expect it to be a big problem, but there are people looking to explore this. But it's mainly for the bineutron stars that it could be an issue.
Yeah, maybe I can add that in RT we are forming teams for the different activities. So in particular, there is an observational science board under realization, and we leave the target to define, of course, in more detail the science of ET, but we'll address this science toward the data analysis. So one of the main targets of this group will be to understand how to resolve the events, if possible, when we have a so high rate in our data.
And as there will, as the mock data challenges will be needed on both sides, I sincerely hope that this will be a joint effort and not something like a competition.
Absolutely, yeah. So I think that you should be able to talk to Satya or Salvo.
Yeah, we are talking
to coordinate. So.
Okay. It seems
Thank you, everybody.
There are no more questions. The problem of many overlapping signals seem not too far from the problems that LISA data analysis will be facing. Is some kind of collaboration foreseen? I wouldn't be aware of a collaboration at the moment, but it is definitely a good idea to do this because, as you say, the problems are similar. So we should keep that in mind.
And Satya is familiar with both, so I'm sure that they'll be working together.
Yeah, also in other groups are mixed groups on LISA and the T, so people is organizing themselves for working on both the detectors.
Yes, but as Michele said, we are at the moment rather focusing on infrastructure and instrument science, and observation science board is yet to come, and then these issues will be addressed as well.
I mean, not so much. I mean, we are forming the OSB in this moment in the steering committee. So I hope that in the first months of the next years, this will be operative. And this means that since the first months of the next year, there will be an action devoted to this activity. So it's for sure we have in emergency, in urgency, for the infrastructure, because it's something that will be we have to defend strongly in April, but all the rest is not less important. It's just a little bit less urgent.
Yes, but for the reason of urgency of infrastructure and instrument, we started with that and OSP to follow. Okay. Good. I would like to thank all the speakers of this session for the nice overview. And tomorrow we'll start, let's see, at 9 o'clock with sites and infrastructure.
Yes. Okay.
Okay, many thanks to all of you for joining, and have a good night or day or wherever you are, and see you tomorrow.
Okay.
Thank you.
Bye.